So let's start the lecture number 5. So previous day we have analyzed the how to test composite hypothesis using Neyman-Pearson fundamental lemma. So let's start today's lecture. We gonna learn in this lecture how to test the variance of a hypothesis. So let's start. So first, a large sample test, for variance and the large sample test for variance. The chi-square test for normal variance is sensitive to the assumption of normality. Of the underlying population. We have another approximate test where n number of sample is large. Let x1, x2, xn be a random sample from a population with variance sigma square. The important thing is here that we are not assuming that the underlying population is normal, so that we lose that assumption now. And to another assumption we have, we don't assume that the underlying population is normal, but another assumption we have taken, that is n is very large. And since we know that the sample mean, sample variance is an unbiased estimator for sigma. From here we can we have that S follows approximately normal, S follows approximately normal with mean sigma and standard deviation sigma square by n, and root over of 2n s minus sigma by sigma follows a normal 0 1 when n is large. Now here hypotheses are H0, null hypothesis is sigma square equal to sigma 0 square, and alternative hypothesis is sigma square not equal to sigma 0 square. So reject test will be reject H0 if mod z, this is z, mod z is greater than z alpha by 2, then at level of significance alpha we can reject the null hypothesis. And similarly the other things that we have learned in the previous lecture that other set of hypothesis will be, this is two-sided hypothesis and one-tailed or one-sided hypothesis. Two type of one-sided hypothesis is here. One is H0 sigma square equal to sigma 0 square and sigma square less than sigma 0 square. H1 is sigma square is greater than sigma 0. Since our test will be based on the alternative hypothesis, so for these two null hypothesis, this and this, the test is same, that is reject H0 if z is greater than z alpha. And another thing is H0 sigma square equal to sigma 0 square, sigma square greater than equal to sigma 0 square. Alternative hypothesis is for both these cases sigma square greater than less than sigma 0, less than sigma 0 square. Then for these two cases test is reject null hypothesis if z is less than minus z alpha. Minus z alpha. Now we will see an example from where it will be clear that our hypothesis, what will be our hypothesis, null hypothesis, it is very important. So we have to choose our null hypothesis in such a way that we can reject it, the acceptance of that hypothesis is very weak. So let me give that example and it will be clear. So example, let x1 x2 xn be a random sample from a population with variance sigma square. It is found that it is from that S is 6.9. we want to test now. You see here my null hypothesis is H0 is sigma less than equal to 7.0 and alternative hypothesis is sigma greater than 7. Now according to our previous theory that when we will reject the null hypothesis when H0 z less than minus z alpha, that means what is z? Root over 2n s minus sigma by sigma, excuse me. So suppose here n equal to 10, then our test statistic will be root 20 into 6.9, that is our sample mean, s minus sigma, that is 7 by 7, and it is negative 0.0639. now reject H0 if z is greater than equal to z alpha. Now you see the for all values of alpha, since it is these distribution sigma s minus sigma by sigma, it is a normal 0-1 distribution. So for any alpha, so here this means it is here, this is minus 0.0639. so you see any significance levels of alpha, suppose any significance level of alpha, this is less than that region. Suppose my alpha is 0.05, then 0.05 alpha means that will be here, that is z alpha, and it is already less than my minus 0.639 is less than this. So this means we will, so H0 cannot be rejected. So this is not satisfied for any significance level of alpha. That's why we will always accept H0. That means we cannot reject H0. Now this is the case for the hypothesis sigma is less than 0.70. Now from this conclusion we can blindly accept that the fact that sigma is less than equal to 7.0. Now let's see another set of null hypothesis. So another set of null hypothesis, one is H0 is sigma greater than 7.0 and H1 is sigma less than 7.0. Now here again you will your state statistic will be the same. Z will be minus 0.0639. and from these we know that we'll reject if z is less than minus z alpha. So if z is less than minus z alpha, and here again you will see any significant level of z alpha is in the range that is very less than this. So that will be here. Suppose alpha is 0.05, so alpha is 0.05 will be here. So that means this is already higher than the any significance level alpha. So that means this is, suppose this is minus z alpha, so you see minus z alpha will be always less than this number. So that means for any significant number alpha, we will accept this accept the hypothesis, null hypothesis. So here also we cannot reject. Okay, so let me rewrite this here. For any reasonable value of alpha, we cannot reject H0. So you see that when we change the null hypothesis, our when we change our null hypothesis, our conclusion will be differ from first. We conclude from that we since we cannot reject the null hypothesis, we conclude that sigma should be less than 7.7.0. Now if we change our hypothesis to this, we will say that we cannot reject this hypothesis sigma greater than 7.0. That's why sigma in the same time from one set of hypothesis is less than 7 and another set of hypothesis is greater than 7. So this cannot be possible. So here you can see the way you will write the hypothesis, it is very important. So we frame the hypothesis in such a way that H0 is a weaker hypothesis accepting H0 is a weaker conclusion. Now another set of, let's say another set of hypothesis. So one is sigma 0, that is null hypothesis, and another is sigma not equal to sigma equal to 7.0 and sigma not equal to 7.0. Okay, Now then for any reasonable, so here our test will be, what will be our test? Let's see, our test is mod z should be greater than z alpha by 2. For 7, what is our z? The value of z will remain same, or test statistic value will be remain same, that is 0.0639. Now you see that for this the reject H0 if mod z is greater than z alpha by 2. If we take modulus of z, it will become 0.0639, and this is 0.0639 is obviously greater than for z alpha by 2, so that is 0.025. suppose it will be certainly greater than 0.025. so then for any reasonable, so let me check the value of 0.025. so let me check what is the value of so I think it is not greater than 0.025, but we will get for any reasonable value of, so say z is z 0.025 is closer to is 0.025 is 1.96, 0.0025 is 1.96. you will see this is certainly less than z 0.025. so for any reasonable value of alpha we cannot reject the null hypothesis. So we conclude that sigma is close to 7.0, and indeed from the observation you can see that sigma is close to 7. So that is our conclusion. So you have to pose your hypothesis, null hypothesis, in such a way that it seems a weaker hypothesis when we have to accepting the H0. So that's it. So now let's go to the two sample case. Now two sample population. Now we'll call two sample population. Two sample population. Two sample population. Now here two samples are x1, x2, xn and y1, y2, yn. Suppose these two are independently, suppose one is m is independently drawn random numbers, and first sample follows, first samples comes from a distribution, normal distribution, that is mu1 sigma 1 square, and seconds came from normal mu2 sigma 2 square. Now often we have to compare between the means of these two distribution. So our first hypothesis will be compare the means. So null hypothesis is here mu1 equal to mu2, and alternative hypothesis is mu1 not equal to mu2. Now here case 1 will be, case 1 is sigma 1 square and sigma 2 square are known. So then x bar will follow a normal distribution with mean mu1 and standard deviation sigma square by n similar m, and y bar will follow a normal distribution with mean mu2 and standard deviation and variance sigma 2 square by n. Now from the linearity property of the normal distribution you will get x bar minus y bar, so will follow normal mu minus mu2 sigma 1 square by m plus sigma 2 square by n. Now from when mu1 equal to mu2, z equal to x bar minus y bar by root over of sigma 1 square by m plus sigma 2 square by n will follow normal 0 1 distribution. So then our test will be, test is reject h naught if modulus fz is greater than equal to z alpha by 2. Now this is the two-sided test. Now what will be the one-sided test? One-sided test, that is here null hypothesis is mu1 equal to mu2 or mu1 is less than mu2 and h naught is mu1 greater than mu2. Here also similar logic follows, since our test is based on alternative hypothesis. Then for both these mu1 equal to mu2 and this mu1 less than mu2, for these two null hypotheses our test will be remain same, and our test is reject H naught if Z greater than Z alpha. And similarly for these mu1 equal to mu2 and mu1 less than mu2, and for another null hypothesis, that is mu1 greater than equal to mu2, for both these two null hypotheses the test will be reject H naught if Z is less than minus Z alpha. So that's it. Now this is the case 1 when sigma 1 square and sigma 2 square both are known. Now we will explore the case where sigma 1 square, the case 2 where sigma 1 square equal to sigma 2 square equal to, suppose sigma square are known. Then x bar square minus y square, so then this is like x bar will follow n mu1 sigma 1 square by m, y bar is n mu2 sigma 2 square by n, and x bar minus y bar minus mu1 minus mu2 by root over of sigma square 1 by m plus 1 by n will follow normal 0 1. So from here you can get the thing when mu1 equal to mu2, you will get mn by m plus n x bar minus y bar by sigma, that is a normal 0 1. And another way is also possible, so let me discuss that way. So I will discuss that way. So another way is, and this is known. Now here now case 3 is sigma 1 square equal to sigma 2 square equal to sigma square but I think it is okay. Let me do it. Okay, that is there. So and then m minus another thing, m minus 1 s1 square by sigma square equal to chi square m minus 1 and n minus 1 s2 square sigma square equal to, this follows chi square m minus 1, these will follow chi square n minus 1. And from the additive property, from additive, so you see uh, so if sigma is known from these statistic and from above these three tested, two-sided and one-sided tested, these three will follow, and you can get the once you will your conclusions. You can draw your conclusion whether you can reject the null hypothesis, or you uh, why you not why there is no reason to reject the null hypothesis. Now now here, here this is the case 3. When sigma 1 square equal to sigma square equal to sigma square, that is unknown. Okay, then we will follow the following method. From additive property of the chi-square test, we know that m minus 1 s1 square plus n minus 1 s2 square sigma square will follow chi-square m plus n minus 2. And suppose that sp square equal to m minus 1 its square plus n minus 1 its square by m plus n minus 2, and you will see that expectation of sp square is sigma square, because you see ss expectation of s1 square will be sigma square, and expectation of s2 square is also sigma square. Now then that will become m minus 1 plus n minus 1, so that is cancel up and down, and it will become expectation of sp square equal to sigma square. And from these and these will get, since this is a chi-square m plus n minus 2, and we know that this by root over mn by m plus n x bar minus y bar by sigma by root over of these, that is sp square by sigma square into m plus n minus 2 okay, this will not be there, so I think this is it. sp square by sigma square will follow a t m plus n minus 2 distribution. That means root over mn phi m plus n x bar minus y bar sp will follow t m plus n minus 2 distribution. Now here H0 null hypothesis is mu1 equal to mu2, and alternative hypothesis is mu1 not equal to mu2. Then our test will be reject H0 if the statistic t modulus t is greater than t m plus n minus 2 comma alpha by 2. This is the both-sided test. Now let's discuss about the one-sided test. There will be two one-sided tests. One is equal to mu2 and mu1 less than equal to mu2, and here the alternative hypothesis is mu1 greater than mu2. For this, reject h0 if t is not, this will be if t is less than tm plus n minus 2 comma alpha, and another is h0 is mu1 greater than mu2 or mu1 greater than mu2. Alternative is mu1 less than mu2. Then reject if t is, here I'm sorry, here t should be greater than, here t should be less than t m plus n minus 2 comma alpha. So that's it. This is minus, this is alpha. Now last thing is if case 4 is sigma 1 square and sigma 2 square are completely unknown, then there is no exact method to do it, but there is a approximate method, that is Smith scattered procedure. That is, test is t equal to x bar minus y bar root over of s1 square by m plus s2 square by n will follow t new approximate under mu1 equal to mu2, and here new is s1 square by m plus s2 square by n, its square by s1 to the power 4 m square m minus 1 plus s2 to the power 4 n square n minus 1. Note that the new need not to be an integer. In this case we may take the integral part of nu. Suppose if nu is 2.4, we will take nu equal to 2. So that's it. Now we will see another thing in today's lecture, that is pair t-test. So up to now, whatever we see in the two sample test, the both samples, that x1 x2 x m and y1 y2 yn, those two are unpaired samples, means those two are not dependent on each other. Now sometimes it may happen sometimes the sample x and y are not independent. Suppose we are want to test the morning versus evening performance of a group of cricketer. Then since the morning test, if we x means the morning test and y means the evening test of a single person, that we cannot say that x and y are independent random variable, but they are dependent on each other. So that makes this vector, this x1 y1 dot dot x and yn is a bivariate normal distribution with mu1 mu2 and sigma 1 square rho sigma 1 sigma 2 rho sigma 1 sigma 2 square. So this is that, and xi minus yi again will follow a univariate normal distribution, that will be mu1 minus mu2 comma sigma 1 square plus sigma 2 square minus 2 rho sigma 1 sigma 2. Suppose this is mu d, this is sigma d. And here again the null hypothesis, if suppose that mu d is 0, that means mu1 equal to mu v, and alternative hypothesis is mu1 not equal to 0. This hypothesis, this is one hypothesis, so there is this. Number 2 hypothesis is mu d is 0 but h1 mu d greater than 0, and third hypothesis is mu d is 0 and alternative, this null hypothesis alternative is mu d less than 0. So this is if this sigma 1 sigma 2 and rho is completely known, then we can follow the previous method to test the hypothesis, null hypothesis. Now suppose that it is unknown, then we will test, suppose that sigma, these tests, these are sigma rho sigma 2, these all are unknown, then we will test t star equal to root n d bar by sd, where t will be 1 by n summation of, this is ti basically xi minus yi, st square will be 1 by n minus 1 summation of ti minus t by its square. under mu equal to 0. So if we not know these sigma 1, sigma 2 and rho, then we will follow these statistic, where these statistics will be difference between x and y, that will follow this. So this will again follow a t distribution, and this t is t star will follow t n minus 1. Therefore we can have a test based on statistic t star. So for the problem 1, that is this is one-sided null hypothesis. So for here, so reject H0 if t star is greater than Tn minus 1 alpha by 2, and for the problem 2, this is a one-sided hypothesis, so greater than 0, so reject H0 if t star greater than equal to Tn minus 1 alpha. And for problem 3, that is this less than 0, so for this problem we will reject H0 if t star is less than equal to minus Tn minus 1 comma alpha. So that's it. Now give me some rule, that is follow that if the experimental units, so you see you can use both these, you can use these tests or these tests. So what should one take? So for that there are two things is there. So if the experimental units are relatively homogeneous, that is small sigma, and the correlation, that is rho, between the pair is small, the gain in precision due to pairing will be offset by the loss of degrees of freedom. So you see, if there is no correlation between them, so we will get a test that is in the order of m plus n minus 2. So that is at least in the order of m plus n minus 2 order. And here you see that is only if both are m and n, so then we'll get only n minus 1, so that is actually half. So that means in if the precision from the precision from this pairing will be offset by the loss of degrees of freedom. So an independent samples of experiment are used. Samples of experiment are used to test. Now, and in the other range, if the experimental units are relatively heterogeneous, that is large sigma, and there is a large correlation between pairs, one should use the pair T test should be used. Okay, that's it. Now, and the other things will be same. And now another thing I want to, so let's discuss another thing we will discuss in the next class, and from then onwards, after that we will start the non-parametric test. So before that we will see the in the next class the testing for variance when mean is unknown. Okay. That we'll discuss in the next class. That's all. So thank you.